extreme programming if you are missing one of the IDs out of that translation file. And so we had a little phase in our deployment pipeline that basically just scanned all of our user interface code, harvested all the tags, and made sure all those IDs were available in our translation file. It took less than a second to run as part of our deployment pipeline, but it gave us confidence that, we're not missing any of the keys for our translation file. And so that's exactly what that was, is a feedback opportunity to make sure that something is in place. Now, you'll notice in this particular picture a blue border around some of these. It's pretty common practice these days that at one stage you'll start doing more aggressive environment and or container or machine provisioning. And once you pick that up, it kind of carries through it out. It doesn't matter where you do that. And here we're doing it at the acceptance testing stage, but it's really just whatever stage is most convenient. So in that stage, so let's say we're several stages in our deployment pipeline, and the stage before this has been successful. And so now it'll trigger this user acceptance stage, which will pull in acceptance test, deployment scripts, and configuration data, pull in any binaries from the artifact repository. Then this first step is configure environment. This is build, use Puppet or Chef to build out a virtual machine, or build a container, or use something like Terraform to build a cloud environment for me to deploy this code on. That's what we mean by configure environment, that we want to get this as close to a production-like environment as possible. So we'll spin that up and then deploy and smoke test our application to it. So deploy your application to it and then send a simple request to make sure that the application is up and running. Then run your entire suite of acceptance tests against that ecosystem. And when that's done, you tear it down and then copy any test reports or metadata, et cetera, over to the artifact repository. So these are end-to-end tests and as close to a production-like environment as you can get. And this is really just, it's a strong philosophical part of these engineering practices, because the sooner you can get it into a production-like environment, the fewer intermediate environments you have to get it running in. And getting it to run in intermediate environments is really just busy work, because at the end of the day, you need it to run in development and production. And anything intermediate is just some sort of staging. And so the closer you can get it to a production-like environment, the faster, the better off you are. And that actually we'll see comes up in the last chapter today. We talk about some engineering practices that let you get things into production as quickly as you possibly can. This is triggered whenever the upstream stage passes, and this is the first real DevOps-centric build, which is another advantage of doing this. In more traditional software projects, when you didn't try to get it to really deploy to production until it was near the end, there were a lot of things that you had to resolve around incompatibilities, version differences in libraries, et cetera. If you're constantly deploying your code to a production-like environment, then you constantly have to evolve that environment and keep it up to date. And so it allows you to do less work. In fact, that is worth mentioning right here. When I was talking about a continuous delivery versus continuous integration, there's an important point here that I failed to make, that I'm coming back to make here, because it's important overall to the class. That not only is continuous integration just easier from a developer standpoint because you don't have this horrible, dreaded integration phase, you actually end up doing less overall work managing versions of your code if you do continuous integration versus the Big Bang integration phase. Because what happens in the Big Bang integration phase is, as all those changes pile up, they get entangled with each other and more entangled, and part of that integration phase is untangling all that junk that has gotten tangled up. I am a consultant by trade, and so I get to see a lot of very broken software in some cases. We have a client who had a feature branch that was over a year old, and they decided ultimately to throw the code away and re-implement it rather than try to merge that feature branch into the code base, because it would take longer to get all those merge conflicts resolved than it would be just to implement the feature from scratch. And so that's a really important lesson that we learned. And in fact, we'll see, keep repeating over and over again, is that not allowing things to get tangled up by themselves allows you more efficiency and less overall work when you're doing continuous integration than if you're doing an integration phase. So this is not really just moving one piece of work from one place to another. This is literally a significantly less amount of work done managing merges in continuous integration versus having a big giant integration phase. We'll see this lesson pop up over and over again. So this is my user acceptance testing phase that I was talking about here. Up until now, I've been assuming that every one of these phases in a deployment pipeline is automated. And we certainly really like automated things in this world. But there's some things on projects that just defy automation, either at least two good reasons for that. One is there's something that is automatable, like regression testing, but your organization just hasn't reached the level of engineering maturity yet to allow you to do that. And so it's just a matter of time until you can build up to being able to do that. But there are other things that just fundamentally defy automation. Like, for example, assessing the legality of a software change. As much as we'd probably like to automate that roll away, we can't, at least not yet. And so deployment pipelines need to be able to facilitate manual stages for things like exploratory testing, which will never automate away because it's a human trying to figure out an innovative way to break your piece of software. And so deployment pipelines can accommodate manual stages. And so this is, just like before, triggered by an upstream stage finishing. And it pulls in version control, deployment scripts and configuration data, pulls in binaries from the artifact repository. The first step here is configure environment exactly like we do in automated stages, so that's not different. Deploy and smoke test your code to that environment. But where this red line is, the little barbell line right there, is whatever manual process you're doing. And that may take hours or days or even weeks. But when that is done, it tears down that environment and then issues a pass-fail, because this manual stage may be followed by another automated stage. So, for example, maybe you have a rule on your project that says after exploratory testing is complete, then move your code over to a scalability test to see if it's a viable release candidate or something like that. So you still report the outcome to the integration server so it can tear down the environment that it is wired up and also report status. Manual stages are pretty common in deployment pipelines. Maybe you don't want to disrupt your UAT environment, and so you want to stage deployments into it. Maybe into integration, you want to not disrupt things. Maybe even production. More about that in just a second. And here we need to talk about the push versus a pull model for deployment pipelines. So when I was talking about them before, I said that deployment pipelines, when a particular stage is successful, it automatically promotes to the next stage, tries to become successful. But that's not good if you have a manual stage, because you don't want to be halfway through exploratory testing and then someone push a new release that wipes out the work that you've been doing. And so push is the automatically promote to the next stage. Pull is having a person say, okay, move this into the next stage. More about that in just a second as well. Notice that even on manual stages, we try to automate as much of the deployment process as possible. A single command or single button click, it's just too cumbersome that if every time you need a build, you need to go find a developer, a live chicken, and a voodoo doll and go through some sort of weird ritual to get this piece of software up and running, you need to automate that as much as possible, even for manual stages, so that a single push button or single terminal command can create the kind of environment that you need. This is a picture from the continuous delivery book of the whole thing in one picture. There's the commit stage that we started with. There's the acceptance testing stage. Notice that some of these stages may run in parallel because this is one of the capabilities of a lot of deployment pipelines. Notice, too, that once we pick up some behavior like configure environment, we don't give that up. We keep doing that over time. In terms of machinery, deployment pipelines are basically continuous integration on steroids, and so a lot of people use continuous integration tools and just wire up a sort of a partial deployment pipeline. There's actually a commercial add-on for Jenkins called CloudBees that allows you to build full deployment pipelines on top of Jenkins. All the tools, Circle CI, et cetera, are building more and more of these deployment pipeline capabilities. There is a completely open source, freely available, very sophisticated deployment pipeline at GoCD, created by ThoughtWorks. Started as a commercial product years ago, but as ThoughtWorks, we had a small commercial software division for a time, but as that went by the wayside, we open sourced GoCD. But all of them work essentially the same way as something like GoCD, which has a server component and it has agents, which are things that run on physical machines or virtual machines or containers. The agent is the thing that interacts with the server piece to define rules for your deployment pipeline. So, for example, here's an example. In the compile and unit testing stage, we're doing unit testing and running Emma, which is code coverage. The advantage of this agent approach is, notice here, I can run functional testing on both Windows and on Linux because I have different agents, and so I define what I'm going to run separately from the agents that actually run that stuff. Here's an alternative picture of a deployment pipeline that starts with very basic code, moves through unit testing, and then functional testing, and then maybe into containerization and testing, and then maybe into a staging environment, etc. So let's talk for a second about the difference between continuous delivery and continuous deployment. A lot of people use those interchangeably, but there is a distinction to be made between those, and it's an important distinction. So notice here, unit, functional, and UAT are all promoting to the next stage. These are all push stages. But right here, staging, I put up a roadblock because I don't want things to automatically promote into staging when they're done with UAT. I want someone to have that happen. This is what's referred to as a pull stage. And that actually, it turns out, is the difference between continuous delivery and continuous deployment. Because in continuous deployment, every stage is a push stage. And so it automatically, every time it gets success, it moves on to the next one. And the last step is go live to production. And that's very aggressive. In fact, it takes some special things to be able to do continuous deployment. We'll talk about some of those things and how to make that less risky, because it sounds, to many of you who aren't doing it, really risky. Turns out you can mitigate a lot of that risk, and I'll talk about how to do that as we go along today. And it may not be exactly what you think, but continuous deployment means that as soon as you check something in, it goes through this gauntlet of tests and it goes live. I'll do a case study late today around GitHub. GitHub is a great example of a very aggressive agile engineering organization. They do continuous deployment. They average 60 deploys a day at GitHub. And so every time a developer makes a change, they check it in and they go live deploy projects 60 times a day. Continuous delivery means it has at least one pull stage, like right here. And that's the fundamental difference between continuous deployment and continuous delivery. The goal is that you have the exact same engineering practices, and that whether you do continuous deployment is really a business decision, not a technology constraint. That's the goal here. In fact, the name continuous delivery for it's a good question from AH. Shouldn't the term be delivered code for continuous delivery? The name, when they were trying to come up with a name for this practice, they didn't really use continuous deployment for obvious reasons. It has an already name. They actually picked up from the Agile Manifesto. The Agile Manifesto says something about the continuous delivery of software, and the authors saw that and said, "Oh, that's a really nice phrase, because that's really the goal, is continuously delivered code." To AH's point here. The point of this is, though, that the part of the engineering practices here is to really do this kind of engineering and automation, because, and this is one of the most important things I'll say in this class, and I'll come back to it several times, and it's really the lesson that we learned from the extreme programming developers. We are gradually building our way to what true engineering is going to look like for software engineering. And it's probably not going to look a lot like the kind of civil engineering or building engineering or structural engineering that we often use as metaphors. We have to build our own practices around engineering. And at least part of that, I believe, is going to be around incremental change and automated verification. Because part of the problem in software is that modern software systems have hundreds of thousands or millions of individual moving pieces. And a lot of those pieces can change quite drastically and change the overall behavior of the system, even with a tiny change. And so sanity in software development is really, can I make a small change somewhere and verify that I haven't broken anything else from that change? That's really what continuous integration does, is it automates as much of that kind of stuff as possible. We relearned that lesson in the DevOps revolution, because what did you have? You had operations people running around, manually installing operating systems and patches. Important things were constantly falling through cracks. How did we solve that? Incrementalism and automation. You build automated machine provisioning. You can make incremental changes, spread those changes out to your whole ecosystem. So we'll see the same thing is true for architectural governance, which we'll touch on a little bit later. And so this is a part of the key to modern engineering practices, is this kind of comprehensive automation. Now, up until now, we've only been talking about code, but databases have to join this party as well. And this is something that in the very early days of Agile software development, this is a big, big headache and sticking point. And in fact, I credit my colleague, Pramod Sadalge, for fighting the good fight here and convincing people that all of these Agile practices do in fact work for relational databases, just like they do for source code. He wrote the Refactored Databases book with Scott Ambler, and has been doing this kind of stuff for a while. And so the general practices of continuous integration, how to do schema changes with tools like FlyawayDB, or a whole bunch of tools now that allow you to do kind of database migrations for schema changes. Those kinds of tools are freely available now. There's a big tool that I'm trying to think of the name of now. It's eluding me for some reason. But there are a lot of tools in the space that allow you to do that. What I want to talk about is a particular sort of tweaked engineering practice that we have on a lot of our projects that do continuous integration for databases. And it's this technique called fast and slow tests. When you have a deployment pipeline, this thing may take a while to run because we're doing all this staging and containerization and all that sort of stuff. And so you don't want your developers to wait for the entire pipeline to run before they start working on the next thing. And that's really what this commit and unit test stage is for, is a quick verification that I haven't broken anything structurally in my code. Now, functional testing is checking requirements, and staging is checking integration points, etc. But the first thing I need to know is, did I break anything structurally in my code? And so, consequently, I'd really like this stage to be as fast as possible, because that's the only really one I'm waiting on as a developer. As soon as it gets past that stage, I know it's structurally okay, and the rest of the deployment pipeline can run and tell me if something's broken later on. And so one of the practices that we have on a lot of our projects is try to make this first stage as fast as possible. And one of the ways to do that is to not reach out to external things. So don't talk to databases, don't talk to integration points, et cetera. Mock and sub everything that's out of process, and it creates really fast set of tests. But if you're going to do that, you're chipping away a little bit at the verification part of the testing. And so hand in hand with that, for the second stage, we say don't mock and sub anything in full database checks, et cetera, integration points, to get a better set of verification. What this does is make this first stage super, super fast as a way of letting people get back to work right away. So here's an example from a project that I worked on that utilized this particular set of engineering practices. And here are two consoles for that code. The front one here these are our functional tests. One in front here, one behind it are unit tests. And so if you look at the unit tests, we run almost 9,000 unit tests in 41 seconds. This is a Ruby on Rails project. So about 9,000 unit tests in 41 seconds. The functional testing at the same time ran about half as many tests and took 248 seconds, which is about 4.5 minutes. So that's the difference between, reaching out to databases, et cetera, and just mocking and stubbing everything, even in a language that's not known to be super performant like a Ruby project. And that's exactly what we're getting at, is MS's observation here that testing operations can take a large amount of time, is a fun challenge in these kind of environments. And that's exactly what this does, is try to not create a bottleneck for testing that takes a long time because it has a huge amount of data or really complicated kind of scenarios to test. And so typically what we do with databases and continuous integration, there's a commit stage, which doesn't talk to the database at all. The acceptance stage then spins up an environment, deploys an app to it, creates a database, and applies schema changes to it using a tool like FlyawayDB or some tool like that. Put test data in those databases and then run tests against them to make sure that everything is working. And if all that works, then tear that environment down and move forward. So continuous integration as an engineering practice started in the early 90s with XP. The continuous integration server started in the late 90s. Continuous deployment actually predates continuous delivery because people were doing that with continuous integration servers. And of course, continuous delivery came out when that book arrived in 2010. And as I mentioned, it really is just updated engineering practices for software development. So that's the definition of continuous delivery. Now, what that means is that engineering practices that I talk about here apply equally almost for continuous delivery and continuous deployment projects, which is nice because you don't have to have a completely different set. It really is a business decision as to exactly how far do we go down this automation path. So now that begs the question, well, okay, if we understand what continuous delivery is, it's really a set of really efficient, automated engineering practices for software projects. That's really what continuous delivery is it's a nice, continuous delivery is a nice encapsulation of that principle on software projects. So now, what characteristics of your architecture make it easier to do that? is our next question that we want to tackle here. MS has got a great point here. And one of the great challenges when you have super dynamic data is, and test data is always a challenge because it's bulky, et cetera. So it's one of the great challenges that we're still dealing with on agile engineering projects. So absolutely, particularly for more and more dynamic data. There's a really interesting approach, if you haven't seen it in MS, it's worth mentioning here, particularly if you have really dynamic data that changes a lot. There's a practice being done in the closure community called generative testing, where what they are doing is instead of running unit tests and doing assertions, they are running hundreds of thousands of tests using all sorts of different inputs and then doing statistical analysis over the outcome of those things. So it's an alternate way, and then you query the output of the test run to see if any boundary conditions triggered anything, and so that's actually quite nice if you have very dynamic data, because you're not making assertions about things. You're actually generating huge amounts of data and then statistically testing to see did any boundary conditions trip anything. So that's generative testing. So let's talk about agile architecture, and because that's really the essence here is what we want is an agile architecture that allows us to do continuous delivery. But here's the problem with agility as an architectural characteristic. One of the points that we make in our Fundamentals of Software Architecture book is that architecture characteristics really should be objectively measurable. And what is the objective measure of agility? Well, there is no objective measure for agility because agility is really describing a whole bunch of interrelated things on a software project. This is what we refer to as a composite architectural characteristic because it is composed of a bunch of other measurable things. So that's one of the things that we encourage people to do in our fundamentals book is take composites like reliability and decompose them into things that are actually measurable, like availability is measurable, and it's an aspect of reliability. Same for agility. If we broke this down, what are things that are actually measurable? So deployability is measurable. How often do we deploy things? How often do we get errors during deployments, et cetera? Testability is also something that's objectively verifiable. But really what they're getting at here is modularity and controlled coupling. That's really what they're asking for when they're asking for an agile architecture. Because think about the goals of agile software development broadly and continuous delivery specifically. I want the ability to make one small change in my code and then verify that that hasn't broken any other thing within my code base. Well, if I've got really good modular code with good encapsulation, then when I make a change, I just need to check the things immediately around it. Whereas if I have a big ball of mud, every change may have a rippling side effect somewhere else. I have to test the entire system. And so having good modularity, well-defined coupling really facilitates this ability to do things like continuous deployment or continuous delivery. So let's talk about a few ways to measure and describe some of these coupling things that are quite useful here, and some actual metrics that are useful to us as architects and some terminology as well. So this is probably one that you're familiar with, cyclomatic complexity, which works for pretty much any structured programming language. This is a metric that Thomas McCabe created back in the early days of structured programming. The formula is edges minus nodes plus 2, where edges are possible pathways through code and nodes are the actual lines themselves. So if you look at this little decision statement we have over here on the left, if you sketch out its edges and nodes view, what you'll see is 8 minus 7 plus 2, so the cyclomatic complexity of this is 3. What this allows you to do is look at and measure the complexity of methods or functions within your code base, which is often a good indicator of several other things that we'll talk about in just a second. But really complex code is generally not good. But you all know that. There's, of course, a shortcoming with this metric in that it doesn't and cannot distinguish between essential versus accidental complexity. Some problems are just really difficult, and some are made accidentally more difficult. And so it cannot distinguish between those things. But in general, even if you have a very complex problem space, having overly complex code is not beneficial for reasons we'll talk about in just a second. There's some other metrics that you can use to evaluate code bases. There's a whole family of these called the Chittimer and Kimmerer object-oriented metric suite that look at things like depth of inheritance tree. Weighted methods per class is the cyclomatic complexity summed for all the methods of a class, since all of these metrics are class level. Afferent and efferent coupling is incoming and outgoing coupling, which we'll talk more about in just a second here. There's a really nice metric in the Chittimer and Kimmerer metric suite called lack of cohesion in methods. And I highlight this one because it has such a terrible description on Wikipedia as to what this thing actually does. In fact, it sounds almost like a Zen riddle. The LCOM is the count of the number of method pairs whose similarity is 0 minus the count of method pairs whose similarity is not 0. Huh? This is actually a slightly better definition. The sum of sets of methods not shared via sharing fields, which also sounds a little bit like a Zen riddle. So what is this trying to tell us, this lack of cohesion metric? So consider a component or class where the M's here are methods and the V's are private fields. A is a very cohesive code base because a lot of the methods use all the private fields, whereas B is a very non-cohesive code base because notice that each method just uses one of those fields. B could easily be split up into 3 separate classes or 3 separate components and not hurt anything. And of course, C has mixed cohesion. And so that's really what this is measuring, is given the opportunity for coupling, are you taking advantage of that, or is it just incidentally kind of lumped together? This is a really useful metric if you're doing something like an architectural restructuring or migration, because one of the things you're always interested in is how cohesive is this thing that a whole bunch of other classes are pointing to, and how easily can I break it apart? So this is an indicator. A high score here indicates that it's easier to break a component or class apart than a low score indicates. A lot of what we deal with architects, of course, are components, which are encapsulations of classes, well-defined sets of operations, represented in most of our ecosystems as either packages or namespaces. Components can be containers for classes. They can also show up as subsystems or layers or services or event processors. Microservices may have components inside them, but microservices may be small enough that we don't even need the extra gathering of components inside them, so it could just be a small set of classes. One of the things that we care about components, one of the things that we can objectively measure is how the coupling characteristics of components, including 2 well-known metrics here: afferent coupling, which is the number of incoming connections to a particular component, and efferent coupling, which is the outgoing connections. These are terrible names, but they were named after graph theory when these were defined way back in the 1980s. And so we're kind of stuck with afferent and efferent coupling because all the tools still refer to these as afferent and efferent coupling. Afferent is incoming, efferent is outgoing. And there are a couple of metrics tools that I'll show you in just a second that let you measure coupling. But I want to talk about something else for just a second, which is connascence. This is from a pretty interesting book called What Every Programmer Should Know About Object-Oriented Design by Miller Page Jones. This was written back in the early 1990s. In fact, 1993 is when I'm wanting to say this book was published. Most of this book is not of very much interest in the current day because he is describing an object-oriented design methodology that basically nobody adopted when he proposed it back in the 90s. But the other cool thing he did in this book is define this term connascence that I want to spend a couple of minutes here talking about. Connascence is really a language for describing coupling. So this is not an actual metrics tool that you run on your code. It's a way of describing how things are coupled together. So you may be familiar with, I'm not exactly sure this is, that may be the Star Trek character, not the name of the scientist. There's a famous thing called the Sapir-Whorf hypothesis, and it's basically that the words that you have for something helps your understanding of that thing. And the premise is that, so for example, people who live in really extreme northern climates tend to have more words for snow than people who live in climates that don't see much snow. I live in Atlanta, Georgia, and so we only have one word for snow there. But in the far northern parts, those languages have a dozen different words for snow, one for snow in the air, one for snow on the ground. So you could argue that they understand snow much more deeply than people from the South. That's basically the Sapir-Whorf hypothesis, that language helps you refine understanding of things. And that's exactly what connascence is useful for. It's a language that helps describe coupling and ways to make it work better. I don't think it's French, to CJ's point. There's a description in the book about where connascence comes from. There is